Hello and welcome back to HK Academy. In the previous videos, we looked at the ideal small signal model of the buck converter and learned how the LC double pole, Q factor, and natural frequency shape the control to output transfer function. In this lesson, we will see how two unavoidable parasitics, the inductor resistance RL and the capacitor ESR, modify the plant model. We will compare each effect step by step, look at how the body diagrams change, and understand why accurate modeling is essential for stable voltage mode control and compensator design. Here is the final form of control to output transfer function GVD of S with included series resistance of inductor. And below it you can see the body diagram computed using the real electrical parameters of our hardware. These values are shown on the left. If you look at the ideal buck converter shown with the blue curve, you can immediately see the fundamental characteristics of the power stage. The low frequency gain. For the ideal case, gain is 19.08 decibels. With the finite inductor resistance, the gain reduces slightly. Then a strong LC resonance peak determined by the quality factor Q. For ideal case, Q factor is 42.3 decibels. A higher Q produces a sharper peak while higher inductor resistance lowers the Q. A minus 40 dB per decade roll off beyond the resonant frequency. This is characteristic of a double pole. Resonant frequency for ideal case is around 22.9 kiloradians per second. A phase drop approaching minus 180 degrees around the resonant frequency. This is the feature that makes voltage mode control challenging. Below the ideal case, we also show two additional responses. The red diagram is one for RL is equal to 10.5 milliohms, a realistic inductor, and green diagram is for RL is equal to 100 milliohms, which is a little bit exaggerated to illustrate the effect. As inductor series resistance increases, the DC gain decreases. The quality factor Q drops significantly, the resonance peak becomes flatter, the LC double pole becomes less pronounced, the phase dip becomes less sharp, and these effects are summarized in the table below. When you compare the ideal power stage to the realistic values, you see that even small parasitic resistances can significantly modify the shape of the plant. Next, we will continue by examining how the ESR of the output capacitor shapes the transfer function. After that, we will combine both parasitics and discuss how they impact the final plant model we use for compensator design. Here at the top you can see the final form of control to output transfer function GVD of S with included ESR of output capacitor. And below it the body diagram computed using the real hardware values already shown on previous slide. You can immediately see the familiar structure of the buck converter power stage. Unlike the inductor DCR case, a capacitor ESR does not affect the DC gain. The quality factor depends on the total series resistance, including RESR. Increasing ESR reduces the Q factor and the resonance peak becomes less sharp. What is now new is that we have the ESR 0. This 0 lifts the magnitude at higher frequencies and adds plus 90 degrees of phase. We have the characteristic minus 40 dB per decade roll off from the LC double pole. This roll-off remains present until it is interrupted by the ESR 0, and then it becomes minus 20 dB per decade. Phase begins to recover after the ESR 0. Without ESR, the phase continues toward minus 180 degrees. With ESR, the 0 introduces positive phase and slightly stabilizes the plant. Below the ideal case, we show two additional curves. Green, where ESR is 60 milliohm. This is realistic capacitor, and red, where ESR is 120 milliohms. This is a little bit exaggerated for illustration. As ESR increases, you can see the ESR 0 moves to a lower frequency, the magnitude begins rising earlier, the phase begins improving earlier, the LC double pole becomes more damped, the resonance peak becomes much smaller, the phase dip is significantly reduced, All of these effects are summarized in the table at the bottom right. So when you compare the ideal power stage with the realistic ESR values, you can clearly see how parasitics reshape the plant. This ESR0 will play a major role when we design the Type 3 compensator, especially in selecting pole and zero locations around the LC resonance. Next, we will continue by examining how the inductor DCR and the capacitor ESR behave when combined in the same model. Here is the control to output transfer function including both the inductor resistance RL and the capacitor ESR. Now we can look at how these parasitics shape the frequency response of our converter. Below transfer function, you can see the Bode diagram computed using the real hardware parameters shown in previous slides. Even with both parasitics included, the fundamental power stage structure is still visible. For our values, DC gain is about 19.03 decibels, and you can clearly see this plateau at the left side of the magnitude plot. With the real parasitic values, the resonance is heavily damped. Instead of a sharp peak, we see only a small bump of about 3.1 decibels, which matches the reduced quality factor shown in the expression. After the LC double pole, the magnitude drops with the expected minus 40 dB per decade slope until we reach the ESR 0. The ESR 0 is at approximately 42 kiloradians per second. Here the slope changes from minus 40 dB per decade to minus 20 dB per decade, and the phase begins to rise. This is the effect of the capacitor ESR. The phase dips to around minus 130 degrees, not minus 180 degrees, because the combined parasitics significantly reduce the quality factor. After the ESR 0, the phase recovers and begins to rise toward minus 90 degrees, as the 0 provides positive phase boost. So, comparing the ideal plant to the realistic case with both RL and RESR, you see a much more damped resonance, a smoother magnitude plot, and a clear ESR 0 that shifts the high frequency behavior. This combined model is the more realistic plant we typically use for designing the Type 3 compensator. Now that we have included both parasitic components, the inductor resistance RL and the capacitor ESR, we can write the complete small signal transfer functions of a buck converter. Here are the final expressions for the control to output transfer function GVD of S, the line to output transfer function GVG of S, and the output impedance Z out of S. Just like before, all three share the same LC denominator, but now you can see two important additions in the numerators. The ESR0, which lifts the magnitude at high frequencies and adds plus 90 degrees of phase, and the modified damping term, which now depends on the load resistance, on the ESR, and on the inductor RL resistance. This reduces the Q factor and softens the resonance peak. The natural frequency omega 0 is also slightly shifted because both parasitics weaken the effective LC stiffness. The key takeaway is RL lowers the Q factor and damps the resonance, while ESR introduces the zero that boosts magnitude and phase at high frequencies. Together, they produce a plant that is much less ideal and much more realistic. If you would like to experiment with these models yourself, including the version with RL and RESR and the complete averaged plant, you can download my free buck converter toolkit on HK Academy. It includes LT-Spice models, Octave scripts, and example C2000 projects so you can reproduce all the plots we discussed today. You will find the link in the description below. Thank you for watching and see you in the next video.